kind of things that we do every week to showcase our improvement and our work so that the whole team gets an understanding of what we do. So now, with my work, I work on what I call vehicle integration. And this is a very general topic, but the way I break it down is into three things. There's hardware integration, inner loop stability, and outer loop state estimation. And each of these are to produce greater capability for vehicles as well as improve its guidance, navigation, and control methods. So I'm first going to start off with hardware integration. The main idea here was that we wanted to be able to design, CAD, and 3D print mounts or any type of device that could go on these vehicles. A lot of these became vehicle specific, but the idea was that if there was a vehicle, really quickly we could draw something up, we could 3D print it, and then we could put it on the vehicle, which will allow us to put on any hardware that we want. So what you see here is actually the model that Lauren was talking about in her video. So the first week, me and her ended up crewing the room, and this has been used as a way to reference the whole flight area. So the first big project that I had to work on in this development was working on the bottom-facing plate. And the idea here was that we want a downward-facing camera as well as a downward-facing optical flow sensor. The ones that we were choosing at the time, which is not necessarily the case now, was the MV Blue Fox camera and the PX4 flow. So what we needed to do was implement this kind of sensors on a green machine, or one of these guys. And my solution to this was to make a bottom plate such that this would be possible. Now, one of the bigger problems that came up when we first started doing this, because one of the first things we really wanted was just to stick a camera right in the center and have it point down. Unfortunately, if you look at vehicles like this, that's exactly where we put the battery. And we want these things to fly. So what we ended up having to do was make space for the battery as well as the parts where it's going to hold. Now, this led to another issue, is that we looked at the dimensions of both the PX4 and the Blue Fox, and neither of them would fit on the rest of the space there. So we had to devise a protrusion, which we ended up making rounded because it was just easier for the printer that way, in order to make sure that there was enough space that we can secure all of it. And now, it's hard to see because the holes are rather small, but there's 4 holes specifically here. And what those are for is for another project that I worked on, which I'm going to talk about in a second, which was the front-facing plate. So, yeah. So basically, this is going to go in a vertical motion, and that means these guys, for the most part, are always going to be pointed down. But we also want to know what's going on when we're facing forward. In this case, we decided that it would be good if we could have something that protrudes outwards that also can connect to the plate, so it can be more rigid, as one part, as close as one part as it really can, so that we can also put on another camera. The one thing that was really a big consideration when working on this was that we wanted to have it extend outwards, because we felt that at some point, if it's too close, you're going to start seeing the arms when it turns and when it's moving around. So it was a big consideration because you didn't want to make it too far extended That way, you're adding weight and you're also changing its center of gravity. So, the next piece of hardware that I worked on was a bracket for the odroid. Now, this wasn't just the odroid. The bracket was made with the intention of two things. It needed to have a computational package as well as a vision package. The vision package being one or two cannons. And as you can see, I have two pictures right there, and they look almost identical. The only difference is that they are made to account for the differences in size between the Odroid C and the Odroid XU3. So yeah, the two mounts here are for the purpose of something like, let's say, the Mars Electric Flyer prototype, where you will have something that you can't always say is going to be in a vertical position, where in this case, you can safely Velcro down your Odroid. You can have your bottom-facing camera for collecting features or any type of visual odometry you want to do, but there also might come a point when you want to go into a cruise flight, and in this place, a camera can be implemented here as well. So that was the idea behind that design. So that was basically all I did when it came to the hardware side. The next thing I moved into was interlude stability in simulators. So the way this started was with focusing on the equations of motion. Right? We wanted to know the rigid body dynamics of any type of vehicle, aerial vehicle, of course, with the hopes of it being the quadcopter. The reason this is important is that when you are designing a method for stability or control laws, this is a near necessary step if the laws are going to become very complex. If you do not have correct control laws, it will crash. So the big question was, can we accurately simulate a vehicle's motion? Now, right here, we took some initial data. This is not so much important to see as proof that it worked, but as a kind of reality check and see if the data was making sense. And when we felt like that was good enough, as we took thrust, inertial acceleration, position, velocity, we decided to figure out some type of benchmark which we could quantify the fact that we believed it worked. So what we ended up doing was we found another equation of motion block, and we looked into the algorithm which it was doing, and the paper that it was cited for. And believing that this was a sufficient benchmark, we compared the two. And all it really was we took ours, we subtracted it from theirs, and saw how close the data was. And when we did that, we found out that it was 0 the whole way through for every single piece of information that we looked at. Last thing that we did with the model was we implemented a sensor model. The idea here was that we wanted to model noisy sensors. And this way, you can get a good difference between the truth and the amount of noise. This was really just a way of visualizing what it would be like if there was noise in your sensors, which there is inevitably going to be. And this is just the graphs of the IMU which we modeled, as well as the GPS. All you're really seeing here is that we just introduced some noise to the model that we already had. So that was all with the modeling, but we wanted to, at the same time, but we weren't completely done with the model. We wanted to introduce a model that would work for this guy right here. And so what we ended up doing was we went in to building 1236, and we took him and we put him on a trifiler. And the way this works is you figure out the approximate center of gravity of him, center of mass. You take the center of mass of the trifiler, you line it up, just like in the picture, and you then rotate the trifiler. One of the big things to note when you do that is you do not want to translate it, because the way the equations to solve for the moment of inertia works, that can cause a lot of discrepancies and error. So all you're really doing is you're just rotating it. You just give it a quick perturbation, and then you're just counting the number of cycles it takes over. Actually, you're timing it for the number of cycles that you've chosen. And as you can see, there was a bunch of cycles that we chose. 10, 20, 50. And we looked and compared the moment of inertia. Now, doing this will only get you the moment of inertia about one axis with one test. So what you're seeing right there is the moment of inertia about the z-axis. Obviously, there's two more. So what we did here was we said, okay, this guy is rather symmetric, so these two axes would be approximately the same. But you can also notice that we weren't sure how much this would affect that calculation. So when we took the next two tests, we had one which was in like a plus sign, and we hanged it up like that, and we did the test about this axis. Then for the next one, as you can see in the picture, looked just like an X. And we rotated it again about that axis. This way, when we could look at the data and try and figure out the correct moment of inertia of this vehicle. So the last part of the work that I did was state estimation. So the big question when I was tasked to do this is to produce a type of filter which could do sensor fusion. So what is sensor fusion? Basically, when you're working with autonomous systems, really many systems, you're going to have different sensors. You're not only going to have GPS, you're not only going to have an IMU. You could have visual odometry, you could have a barometric pressure sensor, it doesn't matter. And each of these will have a different measurement model. Now that can be an issue in filtering when you just want to just throw everything into one filter, because everything's going to have noise. You're going to have to filter it anyway. The question is, well, how do we fuse that? The common method for doing that when it comes to filtering is known as the chi-squared test, as I have up there. Basically, this is just a test where you take that term S, which is your covariance, and all covariance really is just how confident am I in how correct my state is. And if the test says I'm not very confident to a threshold which is determined by the user, it will remove all of that measurement data, or even that model, if that model is just showing that it's giving bad information. So the first filter I worked on was the unscented common filter. The unscented common filter is an implementation that is known for its great accuracy. It's a new kind of filter that everybody's really impressed with, but it's also very computationally expensive. which is why when you're working with things that take up all power, like odroids and IMUs, and you want to make sure that if you're giving this that much computation, it's worth what you're doing. So what we did was we made a MATLAB class of it, and we implemented it. You can see the charts up here. This is our filter's estimate of the state. The thing down here is our filter is the actual true state, and they are within less than a degree of accuracy. So it's very accurate. Last thing was called the multi-state constraint common filter, which is just a really fancy extended common filter. And this was a little different because with the UKF we were looking for a general tool which we can just implement whenever, wherever. This was very specific to a project that one of the PIs was working on. And considering how little time we had, we focused on just getting to him whatever we could. So our focus was the IMU. Because the reason this is a lot different than other EKFs is it specifically is for visual odometry and an IMU and fusing that together in one extended common filter. So what we did is called a dead reckoning approach. This isn't filtering. What this really is we are taking our data and we are propagating it over time. So we are constantly getting a stream of data, and all of this has drift. None of it's been filtered. But we are producing accurate data. Now that all of this needed to be calibrated because the IMU, even if it's off by like half a degree, if there's no calibration, you're just going to have your drift shooting up to infinity at some point. But what you're doing is you're trying to obtain all of this data and then make it accessible. And the way we did this was with our the communication protocol that we use here at the incubator called DDS. And what you do is we record this data. Me and Josh drove to McDonald's and with an IMU and a camera, and we took data of us in the car. And then we have that data now on a computer. This data can then be played back by anybody who has a reader, which is just a piece of code or like of the protocol, which can just take away this data. And anybody in this lab can access it. So let's say Locke is finally finished implementing his multi-state common filter. He can take in this data, he can check, and then he can see how accurate his filter is. Or this can go into the general UKF that we made and are furthering. In that case, yes, you can also see how accurate and how much better that is. And if the extended common filter, which is a lot less computationally expensive, is about the same, then obviously you should go with the extended common filter. So, some lessons learned. I got to work on a lot of projects which, when I was in school, I'd heard a lot about, and a lot of software and stuff. I'd only heard of Simulink, and now I actually got to use it. I'd only heard of unscented common filters, and now I know things. I got to work with Creo, and learned that is much more annoying than Inventor. And I think I know what a quaternion is. But all of these lessons have gotten me to the point where I feel like I was able to integrate what I know into these vehicles. Now, I also want to thank Liz for all the help that she's done. It was very appreciated. And I also want to thank Josh, because he's probably the one that had to be the most bothered by me. And obviously the AI team for all the work that they've done in helping me get all this done. So, any questions?
Excellent job.